we're going to dive into functional programming, and we're going to see a lot of code. So this is going to hopefully will be a good end to your first day at GIDS. One thing to note, as mentioned, I'm a developer advocate at AWS. My passion is functional programming. So I love to figure out how functional programming and cloud and those kinds of things intersect. The place that I've been exploring recently is MCP, the Model Context Protocol, new ways for AIs to integrate with external services and data. And I just posted a blog post about a week ago on MCP and how to come up with agent architecture based on MCP. And that's what that QR code will take you to. So this is kind of the current area of interest, and kind of next phase of this will be exploring how MCP and functional programming can come together. So stay tuned for more content around MCP and hopefully how that intersects with functional programming. Okay, so let's dive into functional programming. We're going to cover a lot of different topics today, but I like to start with like I'm like a typical back-end Java programmer, and learned object-oriented programming. And so it wasn't until somewhat recently that I got into functional programming. And coming into functional programming, I'm like, I've got all these patterns that I know and I'm familiar with and can solve my problems with. And then smart people on the internet say, oh, all you need is functions. That's it. Functional programming. It's in the name. All you need is functions. So simple, right? And that's all you need to know is know how to write a function. And too bad it's not actually that easy, and we'll get into it. One of the things that I think is really at the heart for me around functional programming is like, okay, we've got these things, object-oriented programming can solve these problems. Why functional though? Why is that a better approach? And for me, I think Philip Wadler explains this really well when he says, if you can use math to do something, you should. And there's some great benefits that we get by using math. And functions come out of the world of math. And so there is this mathematical foundation to functional programming that helps us, like in math, have better ability to expect how a thing is going to work. Have expectations around when I call something, it should work in a certain way back. That's how math works, is that we can have laws, we can have expectations around how things should function and work. And so this, for me, it really kind of captures the heart of it, is because back to the bio that we started with, what I want is for our software to be better. And a big part of that, making software better, is making it more deterministic, making it more reliable, and then hopefully getting to a place of better, more higher productivity as part of that. And that's been my journey, is that going into functional programming, knowing that there's this mathematical foundation that underpins the ideas, but then also getting to a place where I'm actually now a lot more productive in functional programming than I ever was with object-oriented programming. But as I said, it's not all easy. It's not just functions. In the world of functional programming, we have a ton of different concepts to address how we actually build real things in functional programming. So the object-oriented people could respond and say, oh, you're making fun and saying, no, it's just functions. Well, in the world of object-oriented programming, it's just objects. Everything's just an object. So this is kind of the dual of the first slide there, was that there are a lot of concepts in functional programming to actually get things done. And so I'm not going to be able to get through the entire list, but I do want to get you started on a journey to understanding some of the concepts of functional programming, so that hopefully then you can then level up to some of the more complicated ones there. Okay, so that's my goal for today, is to start just walking through some of these core concepts, showing how they play out in the real world. So there's another important reason for why hopefully you all are learning some of these concepts of functional programming, is that we can see from Java as an example that over time, I just took the last decade, there's been a number of functional programming concepts that have entered the language of Java. And so, and there's even more to come if we look further out. But there's things like switch expressions. We'll talk about switch expressions today, but what we're seeing in a lot of languages is that many of the concepts that I'll go through that come out of the world of functional programming are entering kind of the mainstream languages in various ways and at different paces. So hopefully, even if you're not in the world of a functional programming language like Scala that I'll be showing today, you'll be able to learn some of these concepts. And as the languages that you're using evolve and add more functional constructs, you'll be able to take advantage of those in more ways. So let's dive into our first concept here is immutability. And so I'm going to be doing showing a bunch of code here in IntelliJ. And so this first example is going to show what immutability is. So this is, I think, one of the foundational concepts of functional programming. And for me, coming from the world of objects, it took me a while to grok immutability because it was just a totally foreign concept. It's like I'm used to just having an object and an instance of something, and when I need to make a change to it, I change it. And that's a pretty simple construct. But there's some benefits when we go to immutability. And immutability is just the ability to create an instance of something and then not have it change. And so in Java, this would be a final. But in the world of Scala or in Kotlin and other ones, we have a way to define an immutable instance of something. So this will be a val. And so if I define a val a equals 1, if I try to set a equals 2, do a mutation, that's a compiler. I'm not able to actually mutate that thing. So if I do want to do a mutation, and this is kind of the weird thing, is that because I can't mutate it, how do I actually get something done? Like all programs are essentially doing some form of mutation. So what I have to do is create a new instance. So I can create a B, which is going to reference my A and change the value of it. So I can say, all right, my B is now a new value that's based on the previous value. So essentially a copy of that initial value. So this is really a core construct of functional programming. And I'll be showing this in a lot of different ways as we go through. But let me talk about just some of the benefits of immutability. So if you're a maybe Java programmer who's used Hibernate, there's a place where the mutability that's kind of just inherent in many of the object-oriented systems that we use actually makes it hard to understand when and how mutation happens. Where in functional programming and with immutability, it's very clear. You can just walk through and see when did a copy get made of this thing, because that's the only way to do a mutation. And so in this example, I've got a person, the person's got a name, and I'm going to create an instance of this person, essentially like calling my database insert. And then I'm going to print the ID, and then I'm going to wait 4 seconds and print the ID again. So let's go debug this thing, and we can actually see what's actually happening. And here we go. Okay, so we're going to create our person. Let's walk through that. We've created our person. We can see it there. The ID is currently null. And then let's, there we called the create. So still we'll see that the ID is still null. So our ID was null. But then we're going to sleep for 4 seconds. And after we sleep for 4 seconds, which we can see all this in the console. Oh, I think it should have been null that first time. Maybe I waited too long to actually continue on. But the ID initially is null, and then after some amount of time, it gets its value set. And this happens a lot with mutable code. Is you don't actually know when and how the mutation is being made. So if you need to debug anything underneath this, it becomes very hard to unravel, like when and where and why and how did this mutation happen. And with immutability, it's very clear. It requires a copy, a new instance, in order to actually mutate something. So it becomes more clear to understand. So there's some other ways. This is what we would do in functional programming is we'd create our person. We're just going to know that like this ID on this instance is going to always be null. And so when we call create person, that's going to then initialize our ID and be able to get it back. So let's continue walking through this so we can see how that works. So we've got our person. We're going to print the ID. We'll see that ID is null. But now we call our create person. And now we'll see that the Sally.id still null. Like that's not going to change because it's immutable. And that's always going to be null. But then when we call the Sally with ID, which is the copy that we've called the create person with, then we'll see that sure enough, we get the ID. And so now we can place some expectations on the behavior of our program, where and how mutation happens. And so that's just one of the benefits of immutability is being able to actually comprehend, understand, be able to look at the code and understand when and how mutation is actually happening, because there is only one way that it can happen, which is making a copy of something. Okay, now the next benefit is with concurrency. So I'm going to just let this continue to run, but what we're doing is we have a mutable variable I, and I'm going to, in parallel, increment that I. And you'll see that the output here from that, after we print I after doing 1,000 iterations of increments, you'll see that it's not what we'd expect. We'd expect 1,000, but it turns out that my computer's really fast, and it was able to actually, in parallel, mutate something that then at the same time being mutated by another thread. And so this essentially was giving us a concurrency mistake, where this is not giving us the behavior that we expected because of concurrent modification to a mutable variable. And so concurrency is another place where immutability doesn't have these sorts of mistakes, because there is no way to do this mutation where multiple threads can be having access to a shared mutable thing. So that's another place that immutability really becomes beneficial, is when you deal with concurrency. Okay, so that's immutability, just our quick intro. We'll see this in a bunch of other ways as we go further. The next construct that is important is expression-oriented. So the typical way that, as an object-oriented developer, Java developer, many other mainstream languages, the typical way that I'm used to programming is with statements. I make statements, and those statements can, if they want to, mutate something. But in the world of functional programming, we like to opt more towards expression-oriented, where instead of using statements that do mutations, if they want, everything is a expression, and an expression can return a value. And so just as an example here, we can have an if expression that returns a value. And so we would be able to assign that if expression to a value. Instead of the typical way that we would do this in Java is to have a mutable variable and then mutate within our if statement. We're going to instead just take the output of the if expression. So if it's true, we're going SS will equal the uppercase, and if it's false, it'll be the lowercase variable there. So this leads to some good benefits here, which we'll walk through. So let me pull up the expression-oriented one. So let's start with our example that we just walked through. You can see I've got my my S, which is an expression, just a string. I've got an expression from my if expression. There's many other ways that we can use expressions. Essentially, in a functional programming language, usually everything is an expression that can be assigned. Even functions are expressions that can be assigned. And then let's look at the kind of the non-functional, non-expression-oriented way that I would do something that would be called like an early return. So in the early return way of doing things, I'm going to have my if statement, and I'm going to return empty if the thing is empty, or I'm going to go into a block where I've got my mutable state, and then I've got another if expression, which mutates that var other, and then returns other. So I think this is pretty typical approach called early returns, and this would be a statement-oriented way to do something. For me, this is actually kind of hard to follow. Maybe it's because I'm now so used to the expression-oriented way of doing things. You'll see that that in Scala, it's kind of graying out the return, because by default in Scala, you don't have to say return. The last kind of value that comes out of an expression is the return value, so you don't have to specify the return. That's why that's grayed out there. But let's look at a more functional expression-oriented way to do this, where I'm going to not specify those returns. I'm going to return it. So if it's empty, that will return the string empty. And then if we're in the else block, it's going to go in this inner kind of if block. And so now, instead of doing the early returns, I'm going to have the logic that just returns the values out. So this is the expression-oriented way to do this. So one, it's a little bit, I think for me, more straightforward to follow, because everything is an expression that returns a value. One side effect to this is that typically in functional programming, you would never have an empty if without an else. You would always have an else, because an if statement needs to produce a value if it's true, and it needs to produce a value if it's false. So that's how we typically do that. But here's one of the cool things that we can do once we go expression-oriented that I think is really important to this approach, is that because now this is just a standalone expression, I can actually refactor that into a standalone function. So it's really easy to pull apart expressions into new functions. And so I can take that kind of nested if block, and I can put it into a just standalone function that takes an s as a parameter. And then what we can do is then refactor this to use that upper or default and pass in my string there. So it becomes really easy now to take any expression and refactor that into its own standalone function. So that's one of the really nice things here about having things based on expressions. Okay, so that's expression-oriented, and your quick intro to that, we'll be seeing a lot of that. Everything that I'll be doing in here is going to use expressions, be expression-oriented. Okay, so now the next topic is pure functions. So you're probably familiar with a function. Function is something that takes an input, returns an output. So that's just your normal function. But in the world of functional programming, we like to have a more specific version of a function that's called a pure function. And a pure function says that what we're going to do is we're going to have a function that can't differ its output based on the input. So if I get an input that is an A, it can't sometimes return a B and sometimes return a C. That is not a pure function if it does it. Still can be a function, just not a pure function. So to be a pure function, it has to, for an A, has to always produce a B every single time you call it. If it ever violates that, it's not a pure function. So you can't have an input of an A and a C always be a B. So that can always, depending on the input, can return the same output, but it can't go the other way. A given input has to always produce the same output. And that's what a pure function is. So pure functions are pretty awesome because they give us some superpowers, which I'll walk through with some code examples. Let's go see here what some of this looks like. So I've got this fun test here. So I've got a function. I'm not going to show you the implementation of it. We can just kind of assume, hey, it's called add one. It's probably a pure function that's going to just add one to whatever the input is. So let's go and debug this thing and see what's actually going to happen here when we run this. Okay, so what do you think? Add one with a parameter of 2. What do you think the output of that's going to be? 3. Let's check it, run it. So 3. Yay, we got 3. Okay, now add one with a parameter of 2. We run this again. What do you think the output's going to be? That's what we would think, but it's actually 4. Yeah. So not a pure function. This is add one is not a pure function. We're not sure what's going on in there, but it's not a pure function. Oh, and now it's null. That's unfortunate. That's definitely not a pure function. Oh, and now this time it threw an illegal state exception. So add one, not a pure function. And hard to tell that. If we go look at the implementation, we can see that there's some mutable state, and we do some things based on the state. Super fun. But yeah, not a pure function. Where'd that one go? Pure functions. There we go. Okay, so that's our example of not a pure function. And one of the things we'll talk about a little bit later, but there typically isn't a way in most functional programming languages today. There's a few that do this, but most don't actually give you a way to express that something is a pure function or not. There's oftentimes just naming conventions that will say that this thing is pure or not. So unfortunately, our current programming languages most of them don't have a good way to do that. So you just have to read the documentation or make some assumptions or use what we'll talk about later with effects to model the pure versus the non-pure functions. Okay, so let's take a look at a different example here. So this one's kind of an interesting one. We've got a simple date formatter, and I'm going to specify some dates. And then I'm going to just call this like thing where I iterate through each of those dates. I parse the date. I then format the date using the simple date formatter. And then I'm going to print the output. So pretty basic there. Let's run this one called 2, and let's check the output there. So, okay, looks like it worked. Like the dates we passed in were the dates that we were able to parse and format. But let's now make this thing parallel. So by making it parallel, it's now going to do this same thing, but now do it in parallel. And sometimes, if we get lucky when it's running in parallel, sometimes every once in a while, we get a nice exception from this thing. And the exception is kind of nonsense. And maybe if you're a Java developer, you already know this, but the simple date formatter and I don't know if it's the parser, the format method, or both, they're not thread safe. And so when you reuse an instance of the simple date formatter, you're actually not using pure functions. And even when they may look like it should be a pure function, there's some state underneath there. And so things can blow up in unexpected ways because of that not being a pure function. So that's kind of fun. Okay, so being able to, with pure functions, have some expectations around every time I provide a input of A, I get a output of B, whatever those may be. That's nice because then we can have some expectations that we can easily write tests for. So I should be able to very easily write tests for my pure functions. Add one, you'll remember, is not a pure function, so that's kind of a weird one. But with pure functions, we should be able to reason much more easily about their behavior, and so we should be able to test pure functions as unit tests much more easily. Another term that you'll hear around pure functions is side effects. So a side effect is if any time the pure function needs to reach outside to the outside world to do anything, then that is not a pure function. So some common examples of that, if I need to talk to an external service, use a REST call. If I need to get something from the clock, if I need to get anything from the file system, if I need to get a random number, those are all examples of side effects. And so anytime you have a side effect, it becomes harder to test, harder to reason about, and is no longer a pure function. So we'll talk about how we address that in functional programming with effects. So one other thing to point out here is that typically in functional programming, to support the ability to have pure functions, we oftentimes will take the possible error situations and encode the errors in a different way than maybe you're used to. So if something throws an exception, that essentially is not a pure function because it is not having that deterministic behavior that we saw with pure functions. So anything that throws an exception, not a pure function. So how do we have some purity around things that can produce errors? Well, what we do is we use a way to represent in a data type the possibility that it is a value or an error. And so let me show an example of this. We have a list. It's got 3 items in it. And then I'm going to use this method here called head. Head is just going to take the first item from the list. And if we run this one, then we should do what we expect and we should get Alice as the result. But what if we go and now have an empty list and we call head? Let's rerun this thing and see what happens. Well, it blows up with a no such element exception. So .head is actually not a pure function. So there is another option that we can use in most languages that support some of the functional programming stuff is you can get back a data type that is either the value that you wanted or is the I don't have that value. And so it's represented in values instead of in exceptions. And so if we run this one with our empty list, we'll see that we get back an actual value that is called none. If we go back to our Alice one, then we'll get back a value that is going to be a sum. And this is, if you're familiar with Java, is an optional, but this allows us the ability to, in types, encode the doesn't exist and the value with a sum and a none. Okay, so that's an important part of maintaining purity is head option would be the pure function for this list, whereas .head would be the impure one. And I have sometimes used .head. I don't always stick to always trying to use only pure functions because maybe I know absolutely for sure that my list is never going to be empty, and so I can safely call .head on it. But it's going to depend on what guarantees you have about the data that you're actually calling those functions on.
That is not.
What is that?
What is the person in the array and this?
Sure. So in this particular list, it is a list, and I can show you the type here. This is a list. Whoops. Come on. It should show up. So trying to get it to show the types. Weird. Oh, it showed up for a second in the night. got rid of it. So this is a list of string. And so I could, instead of making this a list of string, make it a list of option of string. And then I would have to put in some or none here, right? I could make that a none. And then I can make this one a sum, right? Like that. But then I can still call head or head option on it. And I'm going to get back I'll get back the option because now my list is a list of option of string, not a list of string. And then I would need to unwrap that. And so we can actually just run this now. So our first item is a none. And when I call head option on this, what I should get is a sum of a none. And so there we go. There's our sum of a none. There is a way that you can take that thing and flatten it. So we can flatten the sum of a none down into a single thing, which in this case would be a none. Let's try that and see if that flatten works to flatten that stuff down. So there we go. We get a none. If it's a sum of a sum, then we get a sum. And if it's a none, it can't be a none of something. So that would that's how the flatten works. Yeah, good question though. Yeah.
Well, they won't make it out in the list of just a list of things.
So you can't. No, yeah. So the type system is not going to allow that. So see how it's like, hey, you're saying this is a list of string. You're trying to put options in there. And so those types do need to align on that. And so this is where, for me, it's important to have a strong type system along with functional programming. Some people go another direction. They use Clojure, for example, or a Lisp-like language that is dynamic. And so they're not getting both the benefit of the type system and the functional programming, whereas I prefer to get benefits of both. And so I get guarantees like this, where it's like, hey, yeah, you can't put an option into a list of string. So in Java, you would use optional. It would be your, like the option in Scala. Optional is what you'd use in the world of Scala. And then there's others in other languages. So in Kotlin, there's nullability in the type system. So it's kind of like having optional in the type system with a question mark on the type. And then in other languages, many other ways to represent essentially nullability as a value is what this is doing. Okay, let's go back. Good questions. Thank you for asking those. To our next topic, which is function composition. So when we have functions, one of the nice things about functions is, like in math, those functions can be composed together. And so let's look at an example of function composition where I've got a function called upper. It takes a string and returns a string, just as uppercase. I've got a function count, takes a string and returns an int, which just returns the length. And so, of course, I can like nest these together, and it goes from the inside out. So first it's going to do the upper of hello, and then it's going to do count of that value. And so that's just calling a function that calls another function. So all that's going to work as expected. But there's another thing that we can do here, and let's just debug this thing so we can see it. Did I run that with profiling, with code coverage? Oh, and got to get my code all working again there. Let's close that. Okay, let's try this again. Here. Yeah. Okay, so I've got my function, nested function calling, and that's all going to work as we expect, where great, we run that, and we get I is 5. I guess in some languages, uppercase can actually change the length. Otherwise, this is kind of a silly, trivial example. But here's what we can do with function composition, is we can actually define new functions that are chains of functions. So we can chain upper, so we can take that upper function, and this is not the actual calling of the function, it's the definition of the function. And then we can say, and then run the count function. So this is going to give us a new function that's going to run the upper function and then take its output and run it through the count function. And so then we can call that function just like we would call the upper function. And let's just check that thing, make sure that it works. So great. In both cases, we saw 5 and then 5. But so this is just one way to take two different functions, compose them together into a new function. There's another method called currying, I just won't go into crane, but there's some other ways that we can do some composition of functions together. So one of the things in functional programming is we have a different mindset for how we look at a program as being a combination of functions and values. And functions are just things that produce values. So essentially our program is just values. And so we can assign any function and its output to an actual value if we want that kind of intermediary. So that's like this example is showing. But you can also just create the same program by just nesting the function calls. And I did a different syntax in Scala, is just what I'm using. There's a different way to do a function calling syntax. But I think this kind of shows this program is functions is values, is that we're calling print. That's going to call the count function. The count function is going to call the upper function with a parameter hello. And so essentially our whole program becomes this like structure of functions and values. And that's all that a functional programming program is. Okay, so that's our function composition. Now let's go on to higher order functions. So this is where things start to get a little bit trickier and kind of out of the norm of how we do things. And so with higher order functions, and there's fancy names for a lot of these things, and I give you the names like higher order functions just so that when you come across that name, you'll be able to be like, oh yeah, I don't need to remember what a higher order function is, but hopefully the concept you'll remember. So a higher order function is a function that takes a function as an input and or takes a function or returns a function as an output. So here I have a function do something to string, and do something to string, you'll see that one of its parameters is a function. And this is the like short syntax for a function as a parameter. So the function that it takes needs to have an input of a string and an output of a string. And in this case, all we're going to do is call that function with the first S parameter here. And then, of course, we can call our do something to string. We can give it that S parameter, and then we can give it the function that's going to do that change to the string that we gave it. So that's our first higher order function that takes a function as an input. And then there's the return a function that you can then use. And so a good example of this one that gets used in some web frameworks in functional programming is, let's say I want to be able to give a function to something that's going to be a request response handler for like a web request. And so in this particular one, I've got this request handler function, which takes a string, and then it returns a function request response. And so what I'm going to do is take the request that I get in, I'm going to make some modification to it, and then return my response. And so if I, in this first case, call my request handler with a parameter, this just gives me back a function that then I can call. And so my second parameter to this one is the actual request that's going to get passed into my request handler. So this is a pattern that you will see in functional programming for things like request handlers. So that's higher order functions in very quick form. Let's go on to the next one, which is there's the term here is called functor, and it's, again, weird terms in functional programming, but a functor is essentially like I've got something and I want to make some modifications to the stuff inside of this thing. So there's a bunch of different functors, and of course you can build your own, but I want to go through some of the common functors. And this is again a place where it's like, okay, we've got maps, we've got filters, we've got flattens, we've got all these different functors that you can use in functional programming. The way that in object-oriented programming that you do most of this stuff is just with a for loop and mutation. And so again, why is it better? Hopefully that will reveal itself as we go through some of these examples here. But I definitely personally prefer the functional functor approach to doing these kinds of manipulations on data structures. So let's go through this example. I've got a list that's James, Bruce, and Bill. This is my list of people, and we're going to walk through some of the different ways that we can use functors just on a list in this case. So any data type can have functors. I'm going to just show the functors that are associated with a list data structure. So let's create my list. Let's walk through this. So there's my list of people. The first one that I'm going to show is a map. And so you probably are familiar with map from MapReduce or Scala Stream, or sorry, the Java Streams library has map functions. Many libraries now for their collection types have a map. A map is just going to say for each thing inside of this container, so a collection or whatever it may be. So for each thing inside of it, apply this function to change each item and give me back the thing with all of the changed items. So that's what the map function does. So in this case, my map function that I'm going to put into this map function call is going to just uppercase all the items. So let's run through that and see that. Let's check our console output here. There we go. Now we see that my output that I got back out is James, Bruce, and Bill, but all uppercased. So that's the map functor. Then we have a fold, in this case, a fold right. There's usually on things that have either a left to right, some order to them. The fold functor typically will allow you to decide which direction you want to move through the list, but the fold is going to take all of the items in the collection and reduce them down to a single item. And so in the case of my fold, I have to give it the initial value. So with a fold, you have to tell it what's my starting value that I'm going to aggregate on. And then I have a function. My function is going to give me my person, and then total is going to be the running total of this fold. And so then we're going to, for our function, add to the total the length of the person's name. So not super interesting here to add up the length of people's names, but we'll see that, hey, the output is 14. So the important thing is that the fold took all of the items in the data structure and reduced them down to a single item. And we can use a fold for lots of different purposes to do any kind of reduction across the list, like a sum would be another one. So we can actually see the sum. We can do the same thing as this fold right by taking each item and doing a map to turn each item, each name in this list into the length, and then call .sum. And that's going to give us the same output as we saw before, which is the 14. So there we go. See 14 there. So that's our map and sum doing essentially the same thing as a fold. And that's an important thing, is that with the functors, there's often many different ways that you can use the functors. You can use the maps, you can use the folds, you can all sorts of different ways you can do it, and it depends on kind of your use case, which one makes the most sense. So now what about early returns? So I've got this data structure, in my case a list, and I want to, as soon as I find a person whose name starts with the letter J, I want to return it. I don't want to have to process through the whole list. I want to have essentially an early return out of this find. And so what we can do is call the find functor on this list, and the find functor will give me my list sum. So it is returning an optional because maybe it didn't find anything, so it's an optional there. And let's go back to the code. So that's the find functor. Okay, on to early returns from scratch. So you may be wondering, functional programming often is like, okay, if you want to do early returns, you're going to have to get into recursion. And I did come up with the recursive way to do that same find. And so you can iterate through a list recursively, all the items in the list recursively, and stop iterating when you found the thing that you're looking for. That is how you do an early return in a functional way without any mutation. But the nice thing is that often you don't need to do the recursion manually. There's usually higher level functors that will do the same thing for you, like the find method does. And then there are other methods that you can usually use on functional data structures that will give you the same behavior. Okay, another common one is filter. So if I've got a collection and want to do a filter, this one will just apply a function. In my case, just give me all the things that contain the letter J. So let's run through, keep running with that one. So we can see filter. We get, hey, that's the list of James is what the output's my filter. And then here's an important one called flat map. So flat map we'll talk more about in a little bit, but flat map says like, hey, if you want to put some logic into essentially your map function that allows you to return, in my case, an empty list or a list of some items, then we would use a flat map instead of a map. So instead of returning, whereas map, I returned like a string or an int, I can't remember. In this case, I'm going to return a list, and then these get collapsed down into a single list. So I don't have a list of things. I just have a single list. So that's another typical thing. So lots of different functors that exist on lots of the different functional data structures. And again, like in the world of object-oriented programming, you can think of the functors as, for the most part, anything you would do with a for loop. Now you've got a functional way that is usually uses pure functions and allows you to manipulate data structures in a functional way. So that's functors. Okay, let's go on to monads. So monads are one of the places in functional programming where often people are like, whoa, like too far. You've used totally weird terminology, and now I'm totally lost. But I'm going to give it a try at explaining monads. It took me about 5 years of using monads to actually kind of grok monads. So don't expect that you're going to learn monads today. And also, there's this fun thing, which is the curse of the monad. So Douglas Crawford coined this a while back. He said, once you understand monads, you lose the ability to explain it to anyone else. And so it makes it hard for me to teach you monads. But I found a workaround for this, which is the LLMs. So it turns out the LLMs are not they're not affected by the curse of the monad, and so it's kind of cool. I can actually use in my case, Q is the AWS code assistant, and I can use Q and say like, what is a monad? And it actually gives, and I'm sure many of the LLMs will do a good job at this, but it actually gives a good definition of what a monad is, the actual math underneath the monad, the types of monads that typically exist. And so I'm not going to read through all this now, but use your LLMs. Like you've got these great tools, whether lots of different options available to you. This particular one is in the CLI, but there's ones in IDEs. But use your LLMs to help you understand some of these concepts, because usually they do a pretty good job explaining things. Okay, so that's the definition, which we're not going to go into. We're going to look at some code for monads. So here's my way to show one way to use monads. The hard thing about explaining monads is that monads get used in a ton of different ways. It's kind of like the concept of a function. It's just this general way to solve all sorts of different problems. And so I'm going to solve it for one particular problem. Hopefully that helps you see a little bit of what a monad is. But in my case, I've got a map. So a map is, a key and a value. My key is just called key, and my value is just called value. And then I'm going to randomly create an option of a string. So the actual type for my maybe key, if my code hinting works there, is an option of a string. So sometimes I'm going to have an option that says key, and then sometimes I'm going to have a none. Okay? And then I want to use this key, and I want to look up in my map. So if my maybe key is a sum, it has a value, which is key, I'm going to use that key to look up in my settings. I'm going to look up the value associated with the key that's passed in. And so this is where I'm using the flat map, because the flat map, what it does is if I have a key that's set, it's going to then call this function, which is going to take that key, and it's going to run settings.get with that key. But you'll see that the key, or the .get on the map, returns an option as well. And so I could use just map on this, but then if we look at the actual data types, what I get back is an option of a string. And I don't want the nesting of an option of a string. And so the way that I unnest that is to call .flatmap instead of .map. So that's just one kind of use for how I will traverse through multiple sequenced data structures that are of the same type and reduce those down to a single thing. And so it's really about the sequencing that is important. One of the interesting things with monads is that most languages that support monads kind of natively have a syntax to allow you to do that sequencing that I did here with the flat map. So that flat map, I can do that in Scala, it's called a for comprehension. In Haskell, it's called do notation. But there's some way to apply this like sequential, like, okay, if I've got a sum and I want to use that sum to get another thing that's also an option, then I'm going to get that thing, and then I'm going to continue down this chain of calls through these, in my case, option data structures, and then return ultimately just one option from that. So that's just another way to represent essentially the same thing here with the flat map. So it's all about the sequencing is the important thing. If I have a sequence of operations that all are using the same data type, in this case option, and I want to sequence through operations of that data type, then that sequencing can be represented as a monad and used in this what they call monadic way. Okay, so then there's many other data types that are monads. Try is one that can be either a success or a failure. So you can think of this as, instead of exceptions, I can have something that's a try, and the try can succeed with the value, or it can be an exception. So just another monadic data type that I can use in the same way with the for comprehension. Okay, so that's our very quick intro to monads. Essentially, we're just sequencing things. If that didn't make any sense, ask your LLM. Probably does a better job than me explaining it. Okay, so let's go on to the next topic, which is make illegal states unrepresentable. So this is one of the things that, for me, leads to a lot of productivity gains, is that when we can have our program not allow illegal states to be represented, we can actually really reduce the potential bugs that we get into production, because we're not able to actually compile something that's going to allow illegal states. So let's look at some examples of how we can make illegal states unrepresentable. So there's a few things that we can do here. One, you've already seen the option. The option becomes a way that we can take functions. So for instance, if I have my add1 function and I'm just going to add 1 to the integer, what happens if my input to this is a max value int? Then it's going to wrap around to the other side. Maybe I don't want to allow that. Maybe I want to instead have this function return an option of an int to handle the case where my input value is a int max value. And in that case, it's going to return none instead of sum with the value. So that's one way that we can kind of take our surface area and reduce the places that things can produce unexpected results. And of course, you can do that with optional values, with nullable things. But you can also do that with things like IDs. We saw some examples of doing that. You can also do this thing, which I like to do a lot, which is to reduce the surface area of that are possible to given functions. So let's say that I have a function that I really could take any string. Technically, it's just a string, but I don't want to allow anything that's a string type. I want to reduce the ability to only put things that are names into this. And so oftentimes I'll wrap the primitive data types like strings and ints with a data type like name, and I can create these data types in a very lightweight way that's not going to add extra allocation overhead to those things. But now I can't call this thing. If I try to call only name with a string, it's like, no, you need to be more specific about the type that you're trying to pass in here. And instead, we need to pass in a name so we can create our instance of name. And this just will prevent us from making accidental mistakes where it's like, oh, I meant to pass the ID, but I passed the first name, or I meant to pass the first name and instead pass the last name, whatever it may be. This prevents us from making accidental mistakes by passing the wrong parameters into things. So that's just one way to make illegal states unrepresentable in our programs. There's some nice libraries that help us do this better. So one of those is Neotype that exists in Scala, and there's many different kind of implementations of this, but these allow us to, they're called new type libraries. They allow us to put type constraints on types. So what I'm going to do is create a new type called a non-empty string. It has a method called validate. Validate takes an input, which is a string, and then just make sure that it's non-empty. And now, if I try to create a new non-empty string with an empty string, that's actually a compiler. It's not going to let me actually construct a non-empty string from an empty string. So that allows me to have some additional protection around those illegal states. Those aren't going to be able to be validly compiled. If we have a value that exists at runtime, not at compile time like this one, then we can call this non-empty string.make. And then what I get back is an optional. We can see that NEA is going to be, come on, show me the type. It's a option of string essentially. Or, oh, sorry, that's an either. So an either is like an option, just could be an error. Why wasn't it able to make the string or the actual string? Okay, so those are just some of the ways that we can do this make illegal states unrepresentable thing, but definitely an important part of functional programming is trying to make it so that you have less ways for things to break when you get into production. Okay, so let's talk about ADTs and pattern matching. So ADT stands for algebraic data types. And this is definitely an area that many of the programming languages now have integrated algebraic data types into their type system. And so this is something that's pretty generally available in most languages now. But what is an algebraic data type? Algebraic data type is a type with some composition on it. And so we compose types together through an operator. And you may be familiar in the world of math that there are operators like a plus or a minus that allow us to have some rules around how things work. And so we can do the same thing with types. We can apply certain operators to types to create new types that then have some rules around how those types are going to work. So here's a fun quiz question is, when did algebraic data types first appear? Like when was that first in a programming language? So I may have a guess at how long ago this was. This was 50 years ago. I don't know if somebody said it, but 50 years ago was when algebraic data types first were in programming languages, and now they're becoming something that's pretty commonplace. But some of these ideas take a long time in functional programming to kind of reach the mainstream, which is kind of frustrating and fun. But let's take a look at some stuff around ADTs. So ADTs, algebraic data types. Let's start with our first algebraic data type, which is a sum type. And with a sum type, what we can do is we can say, all right, I have a type, in this case, that is either an int or a string. So I've composed a new type which is either, it's a type that is either an int or a string. And so I have, in this case, just a random, getting a random Boolean, and I'm returning either an int or a string. And so if my random managed to be an int, then this is going to be true. If it managed to be a string, this will be true. And then I can also say, is this an instance of int or string? And that's always going to be true in this case. So that is my basic sum type, is just being able to take one type, or it with another, or it with as many types as you want, creates a new data type. But here's an interesting thing about the kind of basic sum type is that if I or a Boolean, that just becomes Boolean. So Boolean or Boolean is just Boolean. So that gets reduced in the case of the basic sum type. But there's some ways that you can define sum types in some other ways. I talked a little bit about the either, but let's say that we wanted something that really was a Boolean or a Boolean. We can put that into a data type called an either, and the either has a left side and a right side, and we can say both sides in this case are Booleans. So that gives us the ability to define a data type, which is also called a tagged union or a discriminated union, which allows us to essentially form a sum type that can discriminate on the type, unlike the just anonymous one. You may have noticed that this is also similar to an enum. Enums in languages that support kind of any data type on an enum, you can create an enum that has, in this case, two different types. This is also can be represented as a sealed class in Java. Now you can do essentially this form of a sum type with a sealed class. So sealed classes allow you to create sum types. Now here's the cool part. Why are sum types awesome? Why are most languages adding them? Usually it's because they're combined with pattern matching. Pattern matching allows us to take one of these types. Remember, our A was an int or a string, and now have a pattern match. In this case, this is an expression, so I could assign this, right, to a value. But the pattern match allows us to traverse through the possible types of our sum type. And in some languages, we can actually get a really cool feature, which is tell us when we haven't matched on all of our cases. So if I can get the cursor there to show me the compiler. Actually, in this case, a compile warning. So the default is going to say, come on, tell me my compile warning. For some reason, not telling me. But there is a compile warning in this case that says that you have not matched on all of the possible types of A because it's an int or a string. And if I only match on int, I'm missing one of the types that exists. And so usually when I'm working in languages that support it, I turn this into a compile error because, back to the make illegal states unrepresentable, I don't want bugs to be able to leak through into production because I forgot to match on some data type. And so we'll go back to that. But pattern matching allows us to work with sum types in this exhaustive checking way. Whereas if I was just doing this with if statements, it would be hard for the compiler to determine if I've checked all of the possible paths or types that the sum type could be. So that's the awesome thing about sum types. There's also a product type. So like the sum type, we can also represent things with another operator, other types, as with an operator. And so I've got a resettable and a growable, and I can have a type that is a resettable and a growable. And so another way to do this would be to create a class that implemented both of those traits or interfaces, and then everyone that wanted to call this thing would have to inherit from that interface. We can do that in a much easier way with product types because I can just create a new abstract product type that has no name that is a resettable and a growable. And so that's using the AND operator. And then I can, of course, use the things that are available there. Okay, and then there's other ways to represent product types. I can do a tuple type, which is basically like a H-list that is compile time sized. And then you can also use case classes or data classes in Kotlin or records in Java to also create product types. Okay, there's some fun history or reasoning behind the name sum and product, but I'm going to skip that because we're almost out of time. Okay, I'm going to skip over polymorphism, which is type classes and applicatives, and talk for just a second about effects. So I've got a talk on Friday where I'll go into a lot more depth about effects. But here's the thing about effects. I've talked about pure functions, immutability, and that's all great, but a real program is going to talk to the outside world in some way, or it's just kind of useless. And so in functional programming, the best way that I know of to represent those things that are the non-pure parts of our program are with something called effects. And I'm going to dive into that in my talk on Friday, what effects are in effect systems. So that's kind of the next level of functional programming is with effects. Okay, just about out of time, but my slides I'll put up on my website. I do have a book on effect-oriented programming if you're interested in that. Also in the talk on Friday. The effect library that I like is called Zio. There are many options in the world of Scala. And so the talk on Friday will go somewhat into Zio and the stuff in Zio. There is a good functional programming library if you're in the world of Kotlin called Arrow, so check out Arrow. And then if you're in the world of TypeScript, there's a really good effect library called Effect, which brings in a lot of the functional programming concepts that you've seen here into the world of TypeScript. So that's what's next. I'm out of time, but I will take any questions afterwards. So hopefully that was useful for you. Hopefully you can get started in functional programming and build some better software. So thank you.